right. Hello, my name is Francisco.
And my name is Zahi, and today we are going to talk to you more about space, just like every other talk here. But for years, public and private institutions have been trying to push humanity forward towards going into deep space. But before we can do that, we need to be able to settle the places right around our neighborhood. And here at FDL, the space resources teams have been trying to incorporate AI to try to find breakthrough solutions that can help those future space exploration efforts. Now, in particular, our team has been working on incorporating AI with multi-robot collaborative systems for exploration, mining, and prospecting. Now, you all might be wondering, why do we need that? We can just ship everything up. But to make this a reality, to even be able to settle the moon, we need to be able to actually get the resources that are there and actually build these habitats that we want. However, building any sort of space infrastructure is a very difficult task, and it's actually riddled with very many problems. But there's one resource that we actually really need to have any sort of settlement flourish. Does anyone know what that is?
Coffee?
No. It's not coffee. You need it for coffee, and that's actually water. Water is one of the most important things for any sort of settlement effort that we want to try to do. Now, water we take for granted. We use it for drinking. We actually use it for any sort of application that we have here. But it's not easy to get, and a lot of worlds do not have it. And we can't really ship it, because here a bottle of water may be like $1, at the airport $5. But actually to ship a bottle of water to space is about $9,000 to $45,000. Now that number jumps when you actually have to ship it to the moon. At some estimates by PT scientists say that's about $500,000. And that's an expensive bottle of water. I don't know. But the one nice thing is that NASA has actually been able to find water on the moon. Now, the moon has capabilities for tons of water that we can use. However, we have no quantitative amount of how much we can. Actually, there is. So the resource prospector team actually wanted to quantify this amount. So they wanted to go to here, which is Hermite A on the North Pole. Now, this is one small crater, but to give you a big size comparison, it's like driving from here to the Googleplex. And that's not too bad, but now imagine if you're driving, it's in complete shadow, and it's minus 300 degrees Fahrenheit. So that's a big problem for them. But we know that within this permanent shadow region that's always occluded from the sun, water is able to freeze and be stable in those areas. So that was the point of the mission. Now, it might seem easy just to put a robot there, but the moon ain't easy. And there are major temperature fluctuations that can go from, in a shadowed region, from minus 300 Fahrenheit to 200 degrees Fahrenheit. So that's a big, major problem. And any sort of solar-powered robot that we want to use is kind of moot at this point, if it ever gets into a shadow. And the dusty terrain doesn't help either, because it can just make our robots stuck.
Thank you. But that is not all. Let me introduce our small friends here. Here you will see the lander. This is we send the rocket, and from here we are going to obtain different rovers. In this case, we are representing the usual mission on the moon. So we have the rover, we have communications, and we send different information to Earth. Of course, we want to make science here. What we want to do is to discover new places in these shadow regions where we can extract new materials. In this way, our robot is going to move there, but not communications inside this crater. So what was our solution? Okay, we are going to offer one relay rover that is going to be in the border of the crater, and is going to establish the communications between the rover, the science rover, and the Earth. Of course, we came to this idea because we explained this. We listened many interviews with specialists like NASA. So at the beginning, they told us, okay, we need to travel to these places. These dark regions are too complicated. We can offer you a solution. Oh, it's quite nice. For sure, we want this solution. Then we say, okay, we will send more robots to the moon. And they start, what? More robots? It's not enough with one? It's impossible. So in this way, we identify the needs. We were able to see that they will need in the future for this multi-agent robot system an automatic trajectory planning for multiple robots on the moon. In this way, just to make an example symmetry with Earth, imagine that every day you are planning how to arrive every day to all your milestones. Okay, you want to go to the laundry, you want to go to the supermarket, you want to pick up your son. So you are traveling different points of interest along of the day. So probably the night before or in the morning, you are thinking, okay, I need to visit this place, and then you have your mission. This is known like the traveling salesman problem, and it's an NP-hard problem. We are going to solve it using informed search algorithms. What it means? That we are going to make different plans to help our rovers to visit the points of interest on the moon. But beyond that, we are going to provide one extra point. It's opportunistic visit of scientific points during this traversal. It means that we are not going to be able only to reach the points that we want to visit. We want to offer to the operators different points of interest that could be useful for their scientific approach. So in this way, we develop different tools, software tools. They are packaged that right now you can get from our GitLab repository, and mainly are divided in three. The Marmot tool is quite funny name. It's multi-agent resource. Oh, I forgot it.
No, I see.
Operational tool. There, this system is fed for the point of interest from the operators, the maps that we need, all the regions that we need to visit, and the most important, what is important for the operator in the mission control here on Earth? What do you want to have? Better communications? Do you want to have less risk to lose your robot, so you are going to be careful with the slopes? Or you just want to traverse and at the end of the day receive the data? Okay, so we take this data, we mix it, and we offer these different trajectory proposals to the operators. Just a quick site of our data set. These are simulated environments from the moon. In the first case, we have communications, different points of communications. In the second one, our map for the slope. And in the third one, our time-dependent shadows. Why? Because this is not like Google Maps. We are not visiting one point to another point, and the route is always there. We are going to be careful with the shadows, okay? So we need to be time-dependent to offer the best solution in each moment during the mission. This is our cost map altogether, and this is the one that we are going to use for generating our A start. Here is the result of our 8 weeks of research. In this case, we are showing different path planning for our operators here in the mission control. In this case, we are dancing between slope, shadows, and communications, different values, different path plannings, but also visiting different points of interest that are quite useful for them. Our future directions, different strategies, of course, because when we are playing with different robots, everyone can play each different role. So we don't want to send one robot for one task. We want to do many tasks, like rescue robots and other robots there. And finally, we want to give our knowledge to NASA Frontier Development Lab, FDL Thank you, all of you, Sarah, James, Saila.
We also want to thank Intel, NASA, and if you can go to the last slide.
Yes.
The rest of our team and our lovely advisors that actually dealt with us for 8 weeks. So thank you all so much.